Hello seniors, today we're going to see electronic assignment number 30, which is about area between two curves. We're going to be applying the same concept that we have learned in the previous classes, where we determined that the integral of a function in a given range of values from a to b gives us the area under the curve, right? But now we're going to see how we can find areas in between two curves, such as in this example, okay? So, objectives. Number one, calculate definite integrals, both analytically and using technology. And number two, find areas under curves between two curves, applying integrals. So this is a new part. We're going to find area between two curves. So it says, if y1 and y2 are continuous on a defined interval from a to b, and y1 is a function greater than y2, that means that the function y1 is above y2, for all x in this interval, then the area between y2 and y1 and y2 from x equals a to x equals b is given by this integral. It's the integral from a to b of the first function, the one that is above, minus the second function, which is a function that is below. So if you take a look at this graph, for example, y1 would be the function that is above. If you look at the shaded area, y1 is a function that is above the shaded area, like it's the roof of the shaded area, while y2 is the floor of the shaded area. So we would find the integral of y1 minus y2. Why? Because you see that the height of each of the infinite rectangles I can trace here is determined by performing y1 minus y2, right? That'll be the different heights of the rectangles traced. So here it says height of each rectangle equals the top curve minus the bottom curve, which is y1 minus y2 in this example. And the width of each rectangle is differential x, right? It's a very, very small width, which when we integrate, we're going to consider that we're drawing infinite rectangles that replicate this shaded area, okay? Then it says, so the area of the rectangle is found by doing the height times the width, right? y1 minus y2 times dx. If we sum, so it says the sum of the areas of an infinite number of rectangles from x equals a to x equals b, the exact area between the two curves would be given by this expression. The integral from a to b of y1 minus y2 times dx. So it's always the function above minus the function below, and we integrate that from a to b. So let's see this in an example. It says, graph the region bounded by the curves y equals x squared minus 2 and y equals negative x. Write down an expression that gives the area of the region and then find the area. Solve this problem without using a GDC. Okay, so I'm going to show you how to solve this, first of all, without using a GDC. So, part A. Let me rewrite both functions. Y would be, the first function is x squared minus 2. I'm going to use blue for the second one. The other function is negative x. Okay, so from your previous knowledge, you should already identify that this first equation or this first function corresponds to a parabola, right? It's a happy face parabola because this term has a positive coefficient, and this negative 2 over here is causing the parabola to be shifted 2 units down, right? So this is a parabola, and in the second case, this is a straight line with a negative slope. So it's a straight line that goes down, basically. So if we do a sketch of this, remember we're not allowed to use calculator for this example. If we do a sketch of this, we're going to have that maybe, I'm going to put negative 2 around here. Here we would have 0. This would be 0, so here we would have our x-axis. So this is x and this is y. So the red function, which is a parabola, a happy face parabola, should look something like this. The vertex there, and then this goes up. Something like that, right? And then this function, the blue one, is a straight line with a negative slope, and it has to pass through the point 0, 0, because it's y equals negative x. So the line would look something like this. Let me see. It should be a 45-degree straight line that crosses through 0, 0. Okay, so I see that I need to extend this a little bit more until it intersects there. So we're going to go up a little bit. Maybe we can extend this a little bit more. There you go. So there we have the two functions. Let me erase this a little bit. Partial. There. So this function is y equals negative x, and the red one is y equals x squared plus 2 minus 2. So this is how we make a quick sketch of the graph. So what are we asked to find? We're asked to find the region bounded by the curves. So you see that both functions are intersecting at 2 points. One here and the other one here. So you see that they bound a region. I'm going to paint that with green, which is what we're asked. We want to find the area bounded by the two curves. So this green shaded region over here is what we want to find. Okay, so the first thing we need to do is find this limits of intersection. This would be the value of a for our integration, and this point over here would be our value b to define our limits of integration, right? So how do I find those two values? Well, I need to find the intersection point. To find the intersection point between two curves, I need to equate both functions. So we're going to say that, I'm going to work with black now. I'm going to say that x squared minus 2 must be equal to negative x, right? We're equating to find intersection points. Let me write that as a title. Intersection points. So we equate and we solve this. We're going to get that this is x squared plus x minus 2 is equal to 0. Remember, this is case 5. A pair of values that multiplied would give me negative 2, and that added would give me positive 1. Those are positive 2 and negative 1. So this is equal to 0. So there we have one solution, x1, which is a, would be the smaller value, which is negative 2. This is equal to negative 2. And the other value, x2, which would be the upper limit of the integral, would be the biggest value, which is positive 1 in this case. Okay, so there we have our limits of integration. We need to integrate this from a equals negative 2 to b equals positive 1 in order to find the shaded region. So how do we do that? We're going to find the integral from negative 2 to 1, which are our limits of integration. And then remember the rule. It's the function above minus the function below. In this case, the function which is above is the blue one. So this would be the function that we would write first. So we would write negative x minus the function we have below, which in this case is the parabola, right? So minus x squared minus 2. That's what we need to do. And we're integrating this, remember, with respect to x. So there we have the definite integral that we need to solve in order to find the green shaded region. Okay, so let's organize this a little bit. This is the same as saying the integral from negative 2 to 1 of negative x minus x squared plus 2 with respect to x. Okay, so now we know how to solve this. Using the concept of the fundamental theorem of calculus and applying definite integrals, this would be equal to, the first integral is negative x squared over 2. The second integral, the integral of negative x squared, that would be negative x cubed over 3. And finally, the integral of positive 2 is just plus 2x. And we need to evaluate this from the lower limit, which is negative 2, to the upper limit, which is positive 1. Okay, so you already know how to do this. Let me take this down here to have more space. I'm going to put it here. I hope this does not confuse. So this would be equal to, we first evaluated with the biggest value, so this would be minus 1 squared divided by 2, minus 1 cubed divided by 3, plus 2 times 1. And then we need to subtract all of this by this same expression, but now evaluated with negative 2. So this would be minus negative 2 squared over 2 minus negative 2 cubed over 3 plus 2 times negative 2. So then if we do this, remember we're not using calculator to solve this, so we need to do this by hand. This would be equal to, let me see, negative 1/2 minus 1/3 plus 2 minus, and here we would have, this is positive 4 divided by 4, that's 2, so negative times negative, that's positive 2 actually, positive 2. Then we have, this is negative 2 cubed, that's negative 8 divided by 3. Then this turns out to be positive, but then it turns out to be negative again. So this would be a minus 8/3. And then this is negative 4. With this negative sign, it becomes positive, so plus 4. Okay, so we need to add up all of these terms in order to get our result. This would be equal to, let's see, for example, 2 plus 2, 4, plus 4, that's 8. 8 plus all of this would be, okay, to avoid wasting time, I'm just going to put the answer here. This is 27/6, which we can simplify to 9/2. You can take your time to do it on your own, but remember we're doing this without a calculator. So that means that the shaded region has 9/2 units squared of area, okay? 9/2, which is 4.5. So that means that the area here has 4.5 units squared of area. Okay, just to check if we're doing this correctly, I'm going to use a calculator, okay, just to see if we did this correctly. So if you take a look at the calculator, now we're gonna go to math. We're gonna find the integral, and we're gonna write the expression, the complete initial expression, which was this one over here, right? We're gonna write negative x minus x squared. Sorry, I'm using the incorrect x. So negative x minus x squared plus 2. And we're evaluating this from negative 2 to 1. So this should give us as a result 4.5. Let's see. Yes, 9/2, which is rewritten as 4.5. That means that we did this area between the two curves correctly, okay? So that's how you work with the calculator in this case. And this is just to verify that we did this correctly, okay? Now let's see part B. Part B says the following. Sketch the graph of the region bounded by the curves f of x, and we have this function, 2 times e to the power of negative x/2, and g of x equals x squared minus 4x. Write down an expression that gives the area of the region and find the area using your GDC. Okay, so we're going to be using the calculator for this part. If you graph both functions, let me show you that in the calculator. This is actually part B. Let me write the information first. We had two functions. The first function is f of x. The first function is f of x equals 2 times e to the power of negative x/2. And the second function is g of x, right here, g of x, which is equal to x squared minus 4x. Okay, so let's graph these two functions using the calculator. We're going to go to menu graph. I'm going to erase this. And we're going to plug in the first function, which is 2 times e to the power of negative x/2. And the second function is x squared minus 4x. If we graph these two functions, let's draw this. We're going to get this. I cannot see this clearly. There, we can see this clearly. Okay, so we have the blue function on top. The blue function is f of x, right? Remember, here we have the first one is blue, the second one is red, right? So the blue one is on top and the red is below. And we want to find this area over here. Okay, so we already know what to do. It's the blue function, the e to the power of negative x/2, minus the red function, which is x squared minus 4x. So the first thing we need to do with the calculator is we need to determine the points of intersection, right? So if we go to shift G solve and intersect, we're going to find the first point of intersection, which we're only looking at the x value, negative 0.584, and the other point of intersection, if we click to the right, is this one over here, 4.064, okay? So let me write this information using the GDC. Using GDC, we graph both functions, and find intersection points. So if we do this, we're going to get the first value of the intersection, which would be a for our integral, which is negative 0.584. And we're going to get our second value, which would be b, which is equal to 4.064 if we round it to 3 decimal places. Okay, so now that we have both limits of integration, we can write the area between the curve, right? So we're going to say between the curves. So we're going to say that this is the integral right here, the integral from the smallest value, negative 0.584, to the largest value, 4.064, of the function on top, which is f of x, right, according to our graph. So we're going to write this as 2 times e to the power of negative x over 2 minus the function that is below, which in this case is the function g of x, right? So minus x squared minus 4x. And we are integrating this with respect to x. Now, you don't have to do this by hand. If we are told that we can use our calculator, we're going to use the calculator, right? So using the calculator, we're going to go to menu 1. And we can write the integral here. We're going to write this as, I'm going to use parentheses, 2 times e to the power of negative x over 2 minus x squared plus 4x. If we round this, if we distribute the negative sign. So we're integrating this from negative 0.584 to 4.064. And we click on execute, and there we have an answer, which is equal to 14.7 units squared. So that's the area between these two curves, which if you take a look at the graph is the green part over there, right? Now I'm going to show you how you can do this using menu graph. If you go to menu graph and you go to the drawing we just did here, there's an option in order to find this area. If you go to shift, let me see, shift and G solve, if you click on the arrow here, you see that you have an integral here. I don't know if all of the calculators have this option, but if you have it, you can click here. And then you can write intersect, right? So the calculator will know that it will find the area from this point. So you click on execute, enter that, and then you go to the other intersection point by clicking on the arrow to the right, and you click on execute. So the calculator automatically calculates the area between both, and you see that we get this value over here, which is 14.74, which is exactly the value of the area we got here, okay, using the other menu of integrals. So that's how you can use your calculator wisely in order to find the area between two curves, okay? So now let's see one last example before we finish with this electronic assignment, which says the following. It says, now we look at cases where y1 and y2 are continuous on the interval a from b, but y1 is not greater or equal than y2 for all the interval. In this case, you must find all the points of intersection and determine which curve is above the other in the intervals determined by the points of intersection. Okay, so let's look at this situation. It says, write down an expression that gives the area of the region between this function and this function, and find the area between those. Okay, if we graph both functions, I'm gonna make this a little bit faster. If you graph both functions using menu graph, right, you should get something like this. And if you analyze this situation, you will see that at first, the red function is above the blue function. So we would have to find first this green region over here, which is from -2 to 0 if you find the intersection points using the calculator again. And then we're going to do another integral where we're going to have the blue function above the red function. So we would have to add one integral from -2 to 0, where the red is above the blue, plus another integral from 0 to 2, in which the blue function is above the red function. So that's the only thing that changes. You should always consider which function is above the other, okay? So just to resume the steps, we're going to use GDC to sketch, and first find intersection point. Find intersection points. Once we do that, we visualize, well, I'm going to write the intersection points. One would be -2, the other gives us 0, and the third intersection point gives us +2. So then we need to realize, or we need to see which function is above the other, right? So to find the area, let me write this down. The area would be, first of all, the red function, which is the parabola here, is above the blue function in the first interval right here, okay? So for this part, we're going to say that this is the integral from -2 to 0 of the parabola, which is x squared minus 2x, according to our problem, minus this function over here, the blue one, right, which is 10x plus x squared minus 3x cubed. Okay, so that's the first part of the area, and this is with respect to x. And then we would need to add this to, we would add the second part, which is from 0 to 2 of the blue function minus the red function. So now it's the opposite, right? It's 10x plus x squared minus 3x cubed minus the parabola, which is x squared minus 2x. And this is integrated with respect to x. So all of this expression is what we would need to solve in order to find the area of this curve, okay? So if you apply if you use the calculator, we would waste too much time doing this by hand. If you use the calculator, you would see that for this first part, you will get as a value 12. And for this second part, you would also get as a value 12. It's a coincidence that they are both the same, but it is not always like that, okay? So finally, we would say that the total area, the green region which is shaded here, is equal to 24 units squared. You can try finding these values on your own using your calculator, and you would see that you will get that result. Now, a mistake is to, let me do this with a different color because this is wrong. A mistake is to say that the complete area is from -2 to 2. If you try doing this from the extreme to the other extreme, you would see that you would get a wrong result. If you do this, let me show you. 10x plus x squared minus 3x cubed dx. If you try doing this on your calculator, you will get as a result 0 units squared. Why? Because we're going to be adding this area plus a negative area here, right? Because we're assuming that the red function is above the blue function, and it's not that way. So you see that you're getting 0 as an answer. You can try this in your calculator and you see that you get 0. So this is an incorrect way to do this. This is not correct. So let me write that here. This is wrong. You need to separate the integrals and always try to identify which function is above the other in order to find the complete area that you're asked in this case, okay? So try doing this on your own with your calculator, and then you see that this is easy, okay? So I hope this was clear, seniors. If not, please let me know. We're gonna clear it up in future live sessions. Thank you and see you.